Hello, everybody, and welcome to the Cosmos Show, place to be if you're curious about the universe. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Here, you can pick the brains of astrophysicists, get advice from a space doctor, find out what astronomers have to say about life, and find out what's going on above your head, all in the same place. So thanks for joining us tonight, and we hope to see you every other Tuesday live at 6 p.m. Mountain Time on Twitch, Facebook, and YouTube. And remember, you can chat your questions to us on Twitch and YouTube, or you can call in using the Zoom login information on your screen. And we would love to hear from you. So text us your comments and questions, or call us and you can talk with us live. It would be a hoot. So we'd love to hear from you. This week's show, we have Tessa Fisher, a PhD candidate in the School of Earth and Science Exploration at Arizona State University. And she studies network theory and how that applies to discovering life on other worlds. And she'll be here to tell us all about it later on. But in the meantime, let's introduce our co-stars. First, postdoctoral scholar from the Simons Observatory, it's Dr. Nick Galitsky.
Hi, everybody.
Hey, Nick. Thanks for being here. Next, new-ish director of education and public outreach at the Vera Rubin Observatory, it's Dr. Lauren Corlees.
Hey, happy to be here.
Thanks for being here, Lauren, and congratulations on your not-so-recent promotion. Thanks for telling us that. Next, medical doctor and founder of Orbital Biodesign, it's Dr. Danny Carroll.
Hi, everybody. Good to be back.
Hey, Danny. And last, but certainly not least, PhD candidate from the University of Chicago and host of her own YouTube show called Nora's Guide to the Galaxy, it's Nora Bailey.
Hey, everyone.
Hey, Nora. All right, well, welcome everybody, and happy Mardi Gras. It's March 1st, so first day of Mardi Gras in New Orleans. I look to see there's no astronomical significance to that whatsoever. So it's really has nothing to do with, but it is Mardi Gras. And if you've never experienced Mardi Gras, it is definitely worth going down there and checking it out. I was down there for my buddy's wedding several years ago, and wow, that was a week for the books. But moving right along, life advice from astronomers. Today, we have a quotation from Elise Meitner, who was a leading Austrian-Swedish physicist, who was one of the first responsible for the discovery of the element protactinium, as well as nuclear fission. And that was while she was working at the Kaiser Wilhelm Institute on radioactivity. And she was actually one of the first to actually provide direct evidence of radioactivity. And she has to tell us today that life need not be easy, provided only that it is not empty. I think that's a provocative exclamation. And so I will turn over to the co-stars and see what they have to say about it.
I was gonna say, I was looking her up, and it's she certainly lived that, because this is discovering fission right before World War II, and it's clearly quite an active life she led during that period, which is fairly impressive. I think I saw that too, that she was the second woman ever to earn a doctorate degree in physics, might have been it. So very impressive.
I guess life need not be easy, but it's nice when it is.
Touche. Yeah, I was thinking about that also. I was like, yes, I do agree, but sometimes it's nice when stuff just kind of flows along for a little while. when you don't
Yeah,
have to wear a hazmat suit. Oh, sorry. Go ahead, Danny.
No, it's okay. I was gonna say, I feel like these are words to live by, honestly, that it's like, if, if what you feel like you're doing with your life is meaningful, it's okay if it's not easy, and if you genuinely feel like you're contributing to something that's bigger than yourself, then that's, in my mind, that's kind of the point. So, go Leafs.
Yeah, I certainly have not selected an easy path for myself over the years. Any of you up for a challenge, start a nonprofit, way harder than getting a PhD. So yeah, I don't really go for easy either. I usually take the hard road, and I think Robert Frost has something to say about that, right?
Yeah, I mean, I guess this actually does strike very close to home for me, because before I went back to grad school, I was working as a consultant, and I was so bored out of my mind every day. And it was really bad for my mental health, to be honest. And going back to grad school definitely hasn't been easy at times, but like the quality of life that I have now, where I actually feel engaged and challenged in what I'm doing is just so much better. And yeah, it was nice to have a pretty easy workload and be making a lot of money, but I really enjoy my day-to-day a lot more now.
Well said. Well said.
Yeah, and I think another part for me too is to evaluate what does it mean for life not to be empty, and that's something that the pandemic oddly really helped with. That it's really great that I'm finding the satisfaction in my job, but to step back and think about all of the other aspects of my life as well, and like tending to those and making sure that those are full, and then they help you when other things get hard, so that you have these other things to fall back on: your family, your friends, your lifestyle habits, things that you like to do. And so thinking of all the ways that your life can be not empty, even just outside of work as well. It was hard. So I decided to like leave Arizona to move to Hawaii just for that reason. Like this piece just felt missing, and it was really bringing me down, and I needed to make a change. And so being able to step back and evaluate like what are ways that my life could be more full has been a surprisingly fun part of the pandemic. Lost some things, gained some others.
Yeah, I feel like there's so many people who have that same sentiment towards the last couple of years, Lauren. I certainly do. I mean, I definitely consider myself exceptionally lucky that the last couple of years for me were, I mean, like, not to be like too like in anybody's face about it, but like they were great. Like I'm an introvert, and like getting to like work at home in my pajamas, like for the most part for 2 years, and keep my job and connect more with my family on Zoom, and connect with people like who I knew from all over the world who I hadn't been connecting with, just like for who knows what reason, and like making that a priority. Like my family and I, like, so my immediate family, my dad, my stepmom, my brother, my sister, my grandmother, my dad's 2 sisters, and some of the other cousins, we just completed our 100th consecutive weekend Zoom session together on Sunday morning. We're actually up to 104 now. Like the last 2 years. I haven't made every one, but there's been a few people who have met like every Sunday morning for the last 2 years. And we have never done that in my entire life. Like not with phone calls, not with family gatherings. So, I mean, I know that a lot of people have really suffered a lot over the last couple of years, but like you, Lauren, I've really had an opportunity to take stock on what was really important to me, and family really came up as something that I didn't even notice the lack of until I really until I noticed it. And now I can't imagine like not connecting, to Zoom on like more or less like weekly basis with my family, and like we're probably gonna keep doing that because it feels so good.
Yeah, I'm hoping that as things get better, we can like figure out what some of the good things that maybe happen for some of us were, and keep those as we maybe find some of the old things that we're missing and bringing them back to. It's not just forgetting all the new things, but trying to find some sort of blend of the two moving forward. Because I'm also hugely introverted. So in some ways, parts of the last 2 years, I'm like, oh, great. A lot of those things I hated doing, but trying to bring back the things that I do miss too. And so.
Yeah. I mean, and like, and this show is an outgrowth of COVID. It doesn't probably would not have happened, you know, if COVID wasn't a thing. So yeah, so many silver linings and blessings from a pretty terrible situation. Funny how that works.
I think like thinking about what Lauren was saying, you know, finding the thing that's like missing in your life and changing it like that. This is going to sound kind of silly maybe, but like, I feel like a lot of people don't necessarily take a moment to stop and be like, I can change my life, right? Like you get locked into, I live here, or this is my job, or this is my career, or, you know, this is just the way my life is. And it's easy to stay in that path, but like you can control a lot more than you might think. And like, it's hard, but definitely making changes. I think people don't realize how much change they can actually make. And it's big and it's scary, but it can have really positive effects.
Yeah, like you have a lot of agency over your life, even if it doesn't feel that way sometimes. So like it's good to remind ourselves of that every once in a while.
I'm feeling overly reminded of that as I'm trying to figure out what I'm going to do with my life.
Sometimes it's overwhelming. You're like, there's too many options. I need like 3, not a million.
I especially feel like, because like being in the military, I didn't have that, right? Like I had very little agency over my life when I was in my early 20s, and like it was scary having to be like, oh, I have to choose where I live now. I have to choose where I like, but it's great. I like it, and I definitely do not miss that about the military.
Well, Nora, I happen to know a great astronomy outreach education in a fantastic mountain town that provides housing for its full-time employees that's hiring right now. So maybe we should talk offline about that.
Good to know, good to know.
Or you can come to Boulder. It's beautiful.
Boulder's nice too, yeah. But yeah, getting back to what we're talking about, I feel like, at least for me, and I think for a lot of other people, I think that the pandemic really helped people realize how much agency they really did have after being forced into having so much change so quickly. And people realize like, oh, like I can totally do that. And it really like, yeah, it was uncomfortable at first to make some abrupt changes, but like really like, it's just fine. Like I can do all kinds of different things that I hadn't thought about, a day ago. So yeah, I also agree that that's been important to me as well. Because now I'm splitting my time between California and Jackson and working remotely, and it's fantastic. And I never would have dreamed of doing that before COVID. Just wasn't even on the cards. Yeah.
For me, it was an opportunity to be really creative. So I think like you guys are saying, where there's this like increased sense of agency when change is kind of forced upon everybody, but it's uncertain what that exactly is going to look like. And so what I ended up doing, I think, is throwing a whole bunch of stuff against a wall, and a lot of it stuck. I think more of it stuck than I was even expecting. But it's been interesting. So yeah, I'm with you though, Sam. It's been a wild ride, but like overwhelmingly positive, I think.
Yeah, for me as well. Any other comments about Elisa's quote? All right, well, let's move along to Astro Advice, or excuse me, to Astro 365. We just did Astro Advice, this day in astrophysics history. So not a coincidence that we picked that quotation that had to do with radioactivity, because on March 1st in 1869, a French engineer, physicist, and Nobel laureate became the first person to discover evidence of radioactivity. And that was Henry, I'm going to butcher his last name, Becquerel. I think is maybe something close to what it should be pronounced as. But he worked with none other than Marie Curie and Pierre Curie, and the two of them and Henry received the 1903 Nobel Prize in Physics for their work on radioactivity. But I guess it all started on March 1st, 1896. And Another really interesting thing today, the Venera 3 became the first craft to impact Venus. That was in 1966. Another interesting space flight this week, March 5th, that was when Voyager 1 flew past Jupiter in 1979. And unfortunately, when Mars 7 failed to go into orbit around Mars and missed the planet, that was on March 6th, 1974. A couple other interesting tidbits. March 10th, the rings of Uranus were discovered. That was 1977, not that long ago. The first extraterrestrial volcano discovered on Io on March 8th, one of the satellites of Jupiter in 1979. And then we do have a couple birthdays. John Herschel was born in March 7th, 1972. And the Italian astronomer Giovanni Schiaparelli discovered canals on Mars on March 4th in 1835. For those of you who don't know that story, he swore that he was seeing evidence of a civilization on Mars with all these lines that he was seeing through his telescope. It turned out to be just geographical formations on the Martian surface, but he drew all these incredibly elaborate lines on the surface of Mars. And I think Percival Lowell also went crazy with that and swore that he also saw those lines on Mars as well. They do not exist. But there were several astronomers of the day who jumped on the bandwagon and all claimed to be seeing these canals on Mars in the early to mid 1800s. What else? Ooh, it was also a second week of March when William Herschel discovered Uranus in 1871, and Percival Lowell, who we were just talking about, this discoverer of Pluto, was born also on March 13th in 1855. Last but not least, March 14th, 2 weeks from today, just before the next Cosmo show, that is the birthday of Albert Einstein in 1879. So lots of fun stuff happening in the first couple weeks of March in the history of astronomy. Curious if any of those events perked the interest of any of the co-stars.
Looking at this one that we have up, and an accidental discovery. I'm wondering what he thought it was initially, because usually you're right, it's an experiment, so you go through all the ways you messed it up, and then finally you figure out that it's something else, right? So very curious about like what the story is from the lab that accidentally discovered radioactivity on photographic plates.
Yeah, I am too. I didn't have a chance to read into it, but yeah, it was some kind of a photography experiment, and there just happened to be some uranium crystals in the emulsion that was being used to expose the photographs, I think basically it was glowing a little bit. So what the problem was, and that wasn't supposed to happen.
I think it's interesting, the story of the Martian canals, because like you said, it was an Italian astronomer who was mapping the surface of Mars, and he used the word canali for channels in Italian, and I don't believe he intended it as a like these are canals, whereas Lowell, like you said, did take it to be canals, and in the press, especially the American press, ran with it. And I think it's just interesting that a lot of that arose from just kind of a mistranslation almost of these natural term channels versus canals. And I think it was around the time of the Panama Canal, some canal that was like relatively famous. So I think like the public was primed for like hearing this word canals and thinking like Martian canals. I just think that's an interesting tidbit.
Good
Oh,
thing the
that's
press
cool.
never misinterprets astronomy discoveries anymore.
Never.
No.
They've cured themselves.
I actually got misquoted a couple weeks ago in an article. Somebody talked to me about light pollution and why it's important to minimize light pollution, not just from an astronomical standpoint for viewing the night sky and research, but from an ecological perspective. And so I was telling them about how several types of insects and birds use moonlight and starlight to navigate. And we're learning more and more about that all the time. In the article, they said that it was important to reduce light pollution so birds and insects didn't confuse starlight with sunlight. I was like, interesting. Very interesting. I'm pretty sure I did not say that. But that's what they quoted me in saying. And I didn't take the time to write a letter to the editor on that one. So if that's out there in the ethers with me having said that. So there you have it. Any other thoughts, provocations, comments on history of astronomy? All right, fair enough. It is time to take a short break, and we will be right back with our guest spot with Tessa Fisher. Enjoy the break, but don't go away. We'll see you soon. Hello, everybody, and welcome back. We're here with our special guest, Tessa Fisher from the University of Arizona, Arizona State University. Tessa, thanks so much for being here.
My pleasure. I'm happy to be here.
Excellent. Well, we're excited to have you. So we would like to start these guest spots off the same way with everyone with the same question, which is, what's the one question that you wish everybody asks you, but nobody ever does?
Probably one I would say that's at least certainly up there. Aside from the fact of, why don't you tell me more about your research, is what's the difference between something that's alive and something that isn't alive? Because in my opinion, it's actually a bit of a trick question. I am very much of the opinion that it's not a binary state between being alive and being not alive. Rather, like many things in life, it exists along a spectrum, where a tree is more alive than a virus, is more alive than a rock, is more alive than a cloud of hydrogen. Because a sort of dirty little secret in the biology community, especially in astrobiology, is that we don't really have like a 100% reliably consistent definition of life or living systems, because every rule you can think of for categorizing something as alive, you can find an exception for. So rather than go that route, I'm just a big believer in let's put it all on the spectrum, and that some things are more alive than other things, and that's just how life is.
Nice. So much for Schrodinger's cat, huh? Well, cool. That's a fantastic answer to that question. I love that. So we know you do network theory, and that you're using that to help identify signs of life on other worlds. But tell us a little bit more about how you got into astrobiology and astronomy, and your path that led you to where you are today.
Well, unsurprisingly, I was a huge fan of science fiction growing up. I believe my mother is mostly responsible for that. I mean, she literally just one day when I was like 12 handed me a box of her like paperback novels from the 60s, 70s, and 80s, and she's just like, here, knock yourself out. I also grew up in Washington, D.C., so I have early memories, well, near Washington, D.C. I have early memories of going to the Air and Space Museum and the Museum of Natural History and just being utterly wowed by everything there. So science was probably in the cards for me from very early on. And then once I hit high school, I discovered, wait, astrobiology is something you can actually do, and immediately was intrigued. And so I got into college at University of Virginia and figured, okay, well, I want to do this for real. Nobody's offering degrees in it right now, so I'm just going to double major in astronomy and biology and cover all my bases. So that's what I did. But my journey to where I am now is actually a bit more windy than that, because I got to grad school and started on my master's and discovered that there, the astrobiology lab at Washington State University was actually in the environmental science department. So despite having never before taken a course in environmental science in my entire life, I ended up getting a master's in the subject, with largely a focus on looking at microbial ecology. And then I went looking for a place to do my PhD and discovered Sarah Walker's lab at Arizona State. I'd met Sarah some years before, and got really intrigued by her ideas about like universal signs or laws of life, and whether or not network theory might be a good way to detect those sort of like motifs, or no matter how exotic the biochemistry might be, we're assuming that life everywhere in the universe is constrained by the same laws of physics that we are, so therefore some certain elements are just going to have to be held in common, just because, again, the nature of the laws of physics. However, at ASU, the lab is considered the purview of the geoscience department. So despite knowing nothing about rocks, I am now getting a PhD in geoscience. So yeah, it's been a little interesting, winding little path. I have, by the time it's over, I'm going to have 4 degrees in 4 different subjects, but I'm certainly well-rounded.
So you got a liberal arts education without even going to liberal arts school. That's fantastic.
Yeah, exactly.
Well, very cool. Well, I am really intrigued to find out more about how you're actually using network theory to search for signs of life, and I'd love to learn more about that.
Okie dokie. Well, I think
Nora's got a question for you, though.
Oh, okay, go for it.
Before you do that, can you take like a step back and maybe tell us what network theory is?
Sure. Yeah. So basically, network theory sounds very complicated, but at its core, it's very simple. Any complicated or complex system that has like multiple subcomponents, your car's engine, the internet, the biochemical reactions in the cell, whatever, can be represented as a network where the different parts are assigned like points or nodes in the terminology of the field, and then depending on how they interact with other parts of the system, you can connect them. So, for the internet, classic example is, different computers are the nodes, the points, and then the connections between them are the links. And so, you draw it out and it looks like a spider web sort of thing. And you can apply that, like I said, to pretty much any complex system. And in our case, you can do it for chemical reactions as well. Essentially, you look at all the chemical reactions that are happening in an atmosphere, and either by just sending a probe down and observing the chemistry going on, or by figuring out, based off of stuff like thermodynamics, what reactions are likely to be occurring. And to create a network, you assign every type of molecule, oxygen, hydrogen, water vapor, whatever's there, et cetera, a point in the network. And then based off of what reactions those molecules participate in with each other, you connect them. And so it's a really intuitive way of kind of like getting a snapshot of the behavior of an entire system. You can do similar things just looking like using like brute force statistical analysis, but this is a much more elegant way of doing it. And it's also a way that doesn't make my head hurt, which I'm in favor of. And once you've done that, you can then like measure certain things about sort of the shape and structure of the network, which have very complicating sounding names like average shortest path length or mean degree. But in reality, like 90% of it is just adding things up. Like mean degree is literally, on average, how many links connect to a given point in the network? Average shortest path length. On average, what's the shortest path between any 2 points in your network? Stuff like that. And those allow you to sort of quantify kind of, again, sort of the shape and structure of the network. And from that, you may be able to infer certain things about the nature of the system. One thing that sort of inspired this research is that if you look at just like the reaction networks of like, say, the chemistry of, I don't know, happening inside a volcano, it looks like sort of a jumbled mess, all these different compounds reacting with each other. However, if you look at the same sort of reaction network for the chemical reactions that happen with inside a living cell, it looks organized. And furthermore, if you do that same sort of analysis for the different reactions in the atmosphere, all the different planets in our solar system, again, most of them look like these just scribbly messes, but Earth looks organized in a very similar way to the reaction network that you see inside cells. And we're wondering if this is, the result of how closely interlinked the Earth's atmosphere and its biosphere is. And naturally, as an astrobiologist, I'm like, well, can we use this to look for life on other planets?
That is super cool. And a fantastic explanation. I really appreciate that. So where is this subfield at right now? And what are like the hopes and dreams and like where things are going at the moment?
We are doing really cutting edge stuff. I am, more through accident than anything else, have found myself apparently the world's foremost expert in network-based atmospheric biosignatures, because no one has done it before, which is exciting, but also sometimes frustrating because a lot of it feels like you're just kind of stabbing in the dark. What we've done so far is that first, sort of as a proof of concept, to find out, okay, looking at these reaction networks, do they actually reflect anything about the real world, or is this just, some very pretty mathematics that doesn't actually correlate to anything in physical reality? We looked at the atmospheres and the reactions happening in them of hot Jupiters, not because we think there's life there, there probably isn't. And for reference, for those of you who don't know, hot Jupiters are just a Jupiter-sized planet that orbits very close to its host star. And we did this in part because the chemistry involved is very simple, because the heat tends to break down anything particularly complicated, and it's pretty much the major driving factor of that, and what's the word I'm looking for? Composition, pretty much like how much hydrogen do you have versus how much carbon do you have in the atmosphere. Those are pretty much the two major driving factors between what causes the chemistry to act like it does in a given hot Jupiter atmosphere. And then the other thing we were looking at is a little bit more complicated, called the vertical mixing coefficient. But basically that just means how mixed is the planet's atmosphere, and in turn, like how far away is it from chemical equilibrium, where nothing interesting is happening. If it's really mixed, interesting things are going to be happening, because you're going to be getting stuff from like colder parts of the atmosphere meeting up with stuff from the warmer parts of the atmosphere, and a bunch of reactions that normally wouldn't be possible can happen. And so we used network theory to see if we could figure out this vertical mixing coefficient just by looking at the reaction network shape and structure. Some of those measurements like mean degree and average source path length that I mentioned earlier, and it turns out we can. So that was really reassuring to find, but that was kind of our proof of concept. And then what we're moving on to now is actually modeling Earth-like planets that have very similar atmospheres, but some of them we've included biology in the model, whether that's methogenic bacteria that are just pumping out lots and lots of methane. We're working on adding photosynthesis to some of them, versus planets that have very similar atmospheres, but don't have life. And in large part, what motivated a lot of this was the fact that we've realized that you can have Earth-like planets that have atmospheres that are very rich in oxygen or methane or any number of gases we normally associate very strongly with biology, but that don't have biology at all, that those gases were produced by a completely non-biological process. And obviously that brings up a real risk of false positives. So we kind of got into network theory because we wanted to see, can we tell between these worlds that, again, have very similar atmospheres, whether or not they have life on them or not. And so far, our initial results, these are very, very preliminary, do seem to suggest that we can, using the network theory approach. So it's been really cool.
That is awesome. And with the James Webb coming online this summer, you might have some really interesting opportunities to test it, right?
Yep, that's what we're hoping. The next phase of the project is seeing how, whether or not we can figure out the network structure just by looking at like sort of spectral data we get from James Webb Space Telescope. Obviously, I'm hoping that we can, but we don't know for sure yet. But if we can, then yeah, that will be, probably become part of sort of the analysis pipeline for the data we're getting back from that telescope.
Very cool. When you were talking about whether the math actually like bears something out in reality, or whether it's just fancy math, where my head went was Max Planck's mathematical tricks to deal with the ultraviolet catastrophe, and then Einstein's realization that actually energy really is quantized. So I hope that you have a similar revelation with your math.
Here's hoping. Here's hoping.
Let me. Any other questions or comments from the co-stars for Tessa?
I was going to ask, like, what are some of the processes that mimic what we think normally would be signatures of life, but are actually just like totally like red herrings?
That is a great question. There are a couple of them. For oxygen, it turns out if you have a planet that has a lot of water on it around a star that has even like relatively moderate ultraviolet light it's putting out, the ultraviolet light can basically hit those water molecules and split them into hydrogen and oxygen. Hydrogen is super lightweight, it's the lightest element. It just zips off into space. The oxygen sticks around, it's heavier. And you let that go on long enough and you can end up with a very oxygen-rich atmosphere on a planet that is completely lifeless. Another one for getting methane is that if it's a relatively young planet, depending on the sort of rocks it's made of, you can get a lot of methane produced by volcanoes. So that can also mimic the presence of more primitive life.
And how do those processes look different? I guess I don't understand how you define the links between things in the neural network. Like, how does that process like get represented differently than, say, photosynthesis?
I threw it onto my slide deck like a few minutes before the show. I don't know if we can access that or not.
You guys must have like the coolest posters.
Yeah, we can go to those slides now.
Yeah.
Just give us 1 sec. We'll get those up. Working on it here.
You're tapping into my love of like diagrams and visually representing
information,
and so that's why I'm so excited to like see what this could look like.
I knew I would need like visual aids for this, so
Yeah.
I put up a couple of them.
Yeah, we'll get it up in just a second.
Yeah, okay. So if someone else has a question in the meantime, I don't know, but
I do actually, if
Great.
we have a sec. I'm curious, so it's fascinating, like this concept is fascinating, and I'm just curious what the component that you find most exciting moving forward, like if there's one thing that you are most eager to see, to explore with this method of evaluating, things for the
I
future,
want
what would
to
that be?
see how it works with radically different biology. Because so far we've just used like Earth-like biology, and the hope is that the strength of this, because again, mentioned this a bit earlier, we're looking for sort of like universal signs of life, that this is going to work even on like say planets that have atmospheres that are dominated by hydrogen, and their metabolic cycle is linked to like ammonia instead of oxygen and carbon dioxide, or planets where the plants produce chlorine instead of oxygen. That's also been speculated about. Really, really weird biochemistry. And to see, do these patterns still emerge even when we're dealing with stuff that's radically different from what we're familiar with?
Thanks.
All right, we've got that diagram up now.
Oh, not seeing it on my screen.
Yeah, you should be able to see like a virtual screen of like all of our little pictures and the image up there.
Oh, okay, I gotcha.
Yeah, that's what everybody else is seeing.
Oh yeah, I see it. Okay, so you actually want to go to the slide after this. This is just like talking about the difficulties of getting spectral data. This is the thing I was talking about. So the network on the left is the network for Mars's atmosphere. And like I said, this is what most of the major atmospheres in our solar system look like if you look at their reaction network. The one on the right is Earth's. And it obviously looks really organized. And the reason we think this is happening, and the reason we see this sort of pattern in biological systems and also in technological systems, it's, same idea behind the wheel and spoke system for like airline routes. Or hub and spoke rather, is that you've only got a couple of like very, very key central points that have a whole lot of things linking into them. And because of that, if one of these points at random happens to fail for some reason, odds are it will not be one of those central points. It'll be one of the outlying ones because they're the vast majority of it. So it actually gives you a degree of resilience and redundancy. So we think that's the general idea of why we think we see these patterns so much in like biochemistry in terms of the reaction networks and again in human engineering. And so it was really cool to see that it shows up in the Earth's atmosphere as well.
That's super cool.
I see how this concept is really generalizable to like pretty much everything, as you were alluding to earlier, to like social media or, like completely unrelated things that are really
a lot of
pretty
it
similarly.
actually, the research originally came out of like looking into people's social networks, and then only later got translated to like chemistry or biology or biochemistry or whatever. But yeah, it's a really versatile approach and you can apply it to any number of problems.
My sister is getting a master's in economics, and we were talking about the application of network theory on economics a couple of weeks ago. It was fascinating.
I can imagine that. Yeah, there could be quite a lot.
Mm-hmm.
think it's cool too because it's tapping into this like visual representation of the relationships, which is this really unique, like powerful thing that our brain just sort of naturally
Yeah.
does, where it like sees all of these patterns in ways that like computers just sort of fail to. It's really neat.
That's one of the things that drew me to it, is because it is very visual in a very intuitive way of
Yeah.
being able to see, oh wow, there's something weird going on here. Where again, yeah, if you're just doing brute force statistics, you may not see that.
Yeah, like tables of numbers isn't going to show you this relationship.
Yeah, exactly.
Yeah.
I guess I want to know a little more what I'm visually looking at. Are these, do I expect each point to be an element or a molecule? And
Yeah, each
kind of
point
want
is
one of
like a
the-
different molecule that's present in the atmosphere. So
and I
water
want one of the
vapor.
central ones on the Earth to be oxygen. Is that right? Or
I'm assuming this is based off of like a previous work back in 2004, which did not document their code very well, unfortunately. I recall that, yeah, it's oxygen and water vapor is one of the other major central points.
So I'm curious, you said you're investigating kind of how the presence of life might affect the network of the atmosphere, basically. Does that include, or like, would you expect to be able to link that if the life was in some sort of like hydrosphere, so like oceanic life or something, would that also have a follow-on effect on the atmosphere, or would this just be for land-based life?
Theoretically, yeah, as long as it's interacting with the atmosphere, you know, because like most of our oxygen comes from algae in the ocean, and a lot of other like gas emissions, dimethyl sulfide, which is another compound that's suggested as like sort of a gas that's strongly associated with life, largely comes from the ocean as well. So yeah, as long as there's some interaction with the surface in some way, you know, as long as it's not like completely buried like kilometers underneath the surface and there's no connection between the atmosphere and the biosphere, we should be able to pick up on it. Yeah.
So like an icy moon ocean, no, but like just a
Yes,
typical
yeah,
surface ocean,
yeah.
yes. Okay,
Yes,
cool,
yes.
thanks.
sorry, Europa.
We can apply, if we're able to get samples from like the ocean of Europa, we could still apply it then. And in fact, one of the other people in my lab did some research applying network theory to looking at sort of the possible biochemistry of Enceladus and its subsurface ocean. But yeah, in my case, I've mostly been focused on the atmospheric stuff.
I think NASA's sending a probe out there to Europa, right? Like 2040?
Yeah, Europa Clipper.
Yeah, Clipper, right. Yeah. Well, I've got another question that's going to steer us in a little bit different direction, but any other comments or questions pertaining to what we were just talking about before I derail us a little bit? All right, I'm curious to get back to the what I really love about your answer to the first question about is it alive or is it dead, and the spectrum that you talked about. I would just love to hear more about your theory about that.
So I will preface this by saying, like, there are other people in my lab who are way more into this sort of thing in terms of like thinking about life as a very abstract physical process. So this is basically based off of a lot of what I've kind of absorbed via osmosis from them. But the the major thing for me is that the defining characteristics of life are going to be A, it reproduces itself, but also B, maintains itself. How should I phrase this? Sort of maintain homeostasis, I guess is the best way of saying it, of, you know, if you have a thing that is a living organism, within that thing, within the physical boundaries of that thing, you're going to have a set of conditions which are going to remain relatively unchanged compared to whatever else is going out in the environment around that thing. This is not always the case. Viruses are kind of an edge case because they reproduce, but they really don't like maintain their own homeostasis because they're not complicated enough to. And that, that's why I do think they're alive, but they're like less alive than like, a tree. But for me, those are the two major hallmarks. And then we can get in about, some people say it not only has to reproduce, it has to be able to undergo Darwinian selection. But then people bring up, well, we can talk about hypothetical biology that uses a different form of evolution and selection. So does that hold the case? Et cetera, et cetera, et cetera. But in broad strokes, it's basically, yeah, it reproduces and it maintains its environment at a state that is not wholly dependent on its surrounding environment.
So I guess, like when I think about that in terms of like the search for life out there in the universe, like I have to ask myself, like, so what are we actually looking for?
Yeah. And I mean, like, I remember years and years ago, I remember someone saying at like an astrobiology conference, and it's stuck with me since then, that, if we found something like a virus on Mars, we'd be ecstatic because we'd be like, this is clearly signs of alien life. Whereas, if you find a virus back here on Earth, there's a whole big debate about whether or not it's actually a living thing or not. But yeah, I tend to be very inclusivist when it comes to what counts as life or not, especially for the purposes of, in terms of, life beyond Earth, because we're going to have to be open-minded.
Yeah. One random question on that, which is more of a science, us as scientists doing these sort of things. Has anyone attempted to quantize how alive something is?
Yes, actually. Another major thing my lab is working on is something called, molecular assembly theory. But basically, and it does scale all the way up to living organisms, but basically how many unique steps does it take to assemble like a given molecule, and in turn assemble an organism. Like it's still in the early stages, but apparently it does correlate pretty well with like being able to tell if a molecule you're looking at is actually the product of life, or if it's just random detritus. Because it turns out that for a lot of biological molecules like DNA, there are a lot of steps involved, and the sort of the index number for how many steps are required is quite high. Whereas if you're looking at like, I don't know, very simple amino acids like alanine, it's like 4 or 5 steps. So yeah, that is at least one attempt I know of to sort of quantify like, okay, how biological is this biology that we're actually looking at? I feel like there have been others, but that's the first one that comes to mind.
Cool. I guess not too surprising.
Tessa, you mentioned earlier that you're really like the world expert in this. I'm curious about like how the reception has been with other astrobiologists to this idea, whether people are like excited or like they think you're going out on a limb.
So far, like, and admittedly, it's a pretty tight-knit field. But with that said, so far the reception's been pretty positive. People are really excited about the results we've been getting. But on the other hand, like, there's still the question of like, okay, this is really cool, but can we practically apply it to like looking at exoplanets? Because it may be the case that this is a really interesting finding, but like it doesn't actually lend itself to like, oh, we can look at the spectra of a planet's atmosphere and say this is what its network structure is. And while even if that's the case, I still think this work has value because, like I said, it does suggest some really interesting things about sort of universal principles of life in terms of like life as a physical phenomenon. but it would be nice if we could actually tie this to like things you can actually observe, practically speaking. So that's kind of like where there's been a bit more skepticism, for lack of a better term, which I think is entirely deserved, because like we still haven't determined that yet or not. But from like just at a conceptual level, people have been really excited about it.
Cool. Well, I'm glad to hear that. We've got just a few minutes left. Tessa, I'm just wondering if there's anything else like we haven't talked about that you wanted to bring up, or what you want to leave us with.
Not that I can think of. This is pretty much what I've been devoting my, blood, sweat, and tears for the last 5 years of my life towards. But yeah, it's kind of like, again, it's the thing that I know best. And yeah, I can't really think of anything else off the top of my head that.
No, that's a great place to leave it. We were actually talking about just about that earlier on in the show. I don't know if you listened into like the quotation we had for today's show. It was about the best life not actually being the easy life, but one that is not empty. So that blood, sweat, and tears is what we all relate to.
My life is many things, but empty is certainly not one of them.
Yeah, nor is it for any of us. Well, any last questions or comments for Tessa before we wrap things up and say goodnight?
Thanks for doing the work that you do. It's really cool. As the lone physician in the group, it's exciting, to think that these are like potentially the building blocks for something that we can't even fathom yet on on the surface of another planet in millennia to come. So it's really exciting.
Well, thank you. Yeah, it's really an invigorating field to be in, even as it can be frustrating sometimes, but you really do get the sense that you're probing at the very edge of current human knowledge.
Yeah, I just think about the first astronomers who like stuck their necks out there thinking they could detect an exosolar planet. And now everyone else is like, yeah, this can't be done. We don't have the technology. And they did it. And now we know of thousands. So may you have the same success.
Here's hoping.
Well, Tessa, thanks so much for being with us this evening. Really appreciate your time. And yeah, thanks for sharing all your what is obvious passion for
thank you.
what you do. Very inspiring stuff. And thanks to all the co-stars for being here as usual. Tessa, we've got a special gift for you for you're here. So Maggie, I'll reach out to you and a thank you gift for your time. So thanks again for being with us, everybody. Thanks to all the folks behind the scenes who make the Cosmos Show possible. Maggie Linder and Gavin, our stream master, the board of directors of Wyoming Stargazing, all of our supporters, and all of you out there who are watching the show. This wouldn't be a great show without you. So thanks so much for being here. And we hope to see you again in a couple weeks. Until then, be well and don't forget to look up. We'll see you next time. Bye.